In this section, we're going to add to the list of functions we already know how to take a derivative of by looking at logarithmic and inverse tangent functions. To derive the formula for the derivative of a logarithmic function, we will use the formula for the derivative of an exponential function that we saw earlier. If you recall, the derivative of b to the x is b to the x times natural log of b. So if we start with the function y equals log of b to the x, we can rewrite it as b to the y equals x. And taking the derivative of both sides of this equation, we would use implicit differentiation. And we get on the left side b to the y times natural log of b, that's the formula we had just seen, multiplied by the derivative of y, which is dy over dx. So again, that's implicit differentiation. On the other side, the derivative of x is just 1. So if I divide both sides by b to the y natural log of b to isolate dy over dx, we get dy over dx equals 1 over b to the y natural log of b. And then if we just kind of clean it up, we get to the formula dy over dx is 1 over x natural log of b. That's replacing b to the y with what we already had established it would equal to, right? So b to the y is equal to the x, and we want our derivative formula to be free of x's on the right side and have the y's only on the left side. And again, that tells us that when we take a derivative of y, which was log of x base b, we end up with 1 over x natural log of b. And that's going to be our formula for taking the derivative of logarithmic functions. We can also extend this rule by changing our log base b to a natural log. And if I convert that as a derivative of a natural log, what we are going to get is that the derivative of a natural log is just 1 over x, because the base is e, and natural log of e would just be 1, so we're only left with 1 over x as the derivative of natural log of x. Now let's look at an example. In this case, we want to take the derivative of natural log of cosine x. And again, as you hopefully remember, to take a derivative of a function that have as a composition of two functions. So in this case, cosine of x is plugged into the natural log. We do need to use the chain rule. So to start with, as we take a derivative of natural log of cosine x, we're going to get 1 over cosine x. That's the derivative of the natural log part, right? So we just saw the derivative of natural log of x would have been 1 over x. So the derivative of natural log of cosine x would be 1 over cosine x. And then we do need to apply the chain rule and take the derivative of the inside function, which was cosine x. And if you recall, derivative of cosine x is a negative sine x. So now we have 1 over cosine x times negative sine x. And we can combine the two fractions together and get negative sine x over cosine x, or as you hopefully remember, sine x over cosine x is cotangent x. So these two together give us negative cotangent x as the derivative of natural log of cosine x. Right, so to start using some of these rules that we just learned, it's a good idea to go back and review some properties of logarithms. If you recall that logarithms, due to being the inverse of exponential functions, follow certain rules that are in line with the rules of exponents. So the first one being that if I'm taking log base b of a product of two variables or two numbers or two expressions, that's going to equal to the sum of the log of those two parts. Right, so we're going to get a log base b of x plus log base b of y. And again, that is due to the rules of exponents, where if two things are multiplied by each other, the exponents are added, right? As long as the bases are the same. And using the same logic, if I have a division of x over y, that is going to give me log of x base b minus log of y base b. And once again, it's consistent with the rules for exponents. If two expressions are divided with this and have the same base, the exponents are subtracted. And finally, the third rule that we are going to use tells us that if I'm taking a log base b of an expression to a power, I can take that power and make it a coefficient of the log. And so if I have x to the n can come to the front of the log and gets multiplied by log base b of x. And again, the rules would also work for natural logs, and that's really how we are going to use them going forward. So the next thing we're going to look at is what we refer to as a logarithmic integration. Right, so here are the steps we're going to take, and that logarithmic integration allows me to avoid the product rule, quotient rule, and in some cases the chain rule when I have an expression that's made up of a bunch of multiplications and divisions. Right, so this is what we're going to do when we use this logarithmic differentiation. So the first step would be to take the natural log of both sides of an equation, y equals f of x, and then use the laws of logarithms to simplify. Right, so the properties we just saw, we're going to use to simplify our expression. Then we're going to take the derivative of both sides implicitly with respect to x, and then solve the resulting equation for y prime. Okay, so again, looking at an example of how it's used and when it's used. So here's a problem we want to take a derivative of. And as you notice, the expression on the right side is rather complicated. It involves a square root, involves a product in the numerator, and then the denominator, I have an expression that has an exponent. So it would need product rule, quotient rule, and the chain rule. And again, it's doable. It's just going to be a lot more work if we don't use logarithmic differentiation. But again, the key is that the pieces of this are not added or subtracted. They're multiplied and divided. And that was what gives me the ability to use our properties of logs. Right. So first thing, as we saw, the first step is to take the natural log of both sides. Right, so I'm just putting a natural log on both sides of this, and then we are going to apply the log properties to simplify this. So the product here becomes an addition, and the division becomes a subtraction, and I've also rewritten the square root as a power of 1/2. Okay, so next thing we'll do is deal with the exponents, use the third property that we saw. So the exponents can come to the front and become coefficients. So we have a 1/2 natural log of x plus 3 instead of natural log of x plus 3 to the 1/2. And then the exponent 2 has moved to the front and has become a coefficient. So now what we're going to do is take this expression and take the derivative of both sides. And on the left side, it needs to be implicit because we're taking the derivative with respect to x. So left side, I have 1 over y, dy over dx. And on the other side, we're going to use the derivative of log rules, and along with chain rule for two of these things. So for a natural log of 7x plus 5, we get 1 over 7x plus 5 times the derivative of the inside, which is 7, plus 1/2 natural log of x plus 3 gives us 1/2 times 1 over x plus 3. And 2 natural log of x cubed minus 5 gives us 2 times 1 over x cubed minus 5, multiplied by the derivative of the inside. Again, that's the chain rule, and that derivative inside is 3x squared. Okay, so next is a matter of cleaning this up now. So I have 1 over y dy over dx equals, I can combine the two middle fractions into 1 over 2x plus 3. The 7 in the first fraction ends up on the top, and on the last fraction, 2 times 3x squared is 6x squared, and that ends up in the numerator. Right? Now remember, the third step was to solve this for y prime, or in this case dy over dx is how we've the notation we've used. So multiply both sides of this equation by y. I have dy over dx is y times the expression we just had on the right side. And last thing we always want to do is, when possible, replace the y with the equivalent function in terms of x. Our initial problem didn't have any y's on the right side, only had x's. We chose to rewrite it in logarithmic format, but our answer should be back in terms of x's. So we're going to replace the y with the expression that it was equal to when we first started this problem, which was 7x plus 5 square root of x plus 3 over x cubed minus 5 squared. Okay, so let's look at one more example before we move to inverse tangents. Here's another example. We want to differentiate y equals x to the 5x plus 7. Now, remember, we already know how to differentiate x to a power, but as long as that power is a constant, the power rule said if I have x to the 9th power, I would get 9x to the 8th, but that required the exponent to be a constant. We also have a rule for taking derivative of exponential functions. If I had 2 to the 5x plus 7, I would know how to take a derivative of, right? But we don't have a way to take a derivative of a function that has variables both at its base and at its power. And here's when the logarithmic differentiation comes in handy. So we'll take the log of both sides, and again, natural log is easier than using any other base. So we take a natural log of both sides. That allows us to address this exponent and move it to the front. So I get 5x plus 7 times natural log of x. And now I can take the derivative because I don't have that situation where I have a base that's a variable and a power that's a variable. And on the right side, I do need to use the product rule. It is a multiplication. On the left side, I'd have to use implicit differentiation. So natural log of y's derivative would be 1 over y times dy over dx. And as I said, on the right side, we apply the product rule. Derivative of 5x plus 7 is 1 over 5x plus 7 times the derivative of 5x plus 7, which is 5. Right, so that's the derivative of the first times the second. Right, if you recall, that's what the product rule tells me to do. Plus derivative of the second function, derivative of natural log of x is 1 over x multiplied by 5x plus 7. So next we're going to clean up the right side of this expression and put the fractions together. We are going to end up with 5 natural log of x over 5x plus 7. That's combining the 5 and natural log of x on top of 5x plus 7. And again, combining these two fractions together, I get 5x plus 7 over x. Right, so now we're ready to solve for dy over dx. Multiply both sides by y, and then replace y with the expression that we had started with. Remember, y was equal to x to the power of 5x plus 7, so I can replace it and get the final derivative of this function in terms of x only. Okay, now let's look at how we would differentiate the inverse tangent function. So the idea is very similar to differentiating an exponential function. We're going to use the inverse function and then use implicit differentiation. But before we do that, let's review some information about how tangent inverses work. So again, if you remember, if I have tangent inverse of x equals y, that means that if I take tangent of y, I am going to get x, right? That's the definition of what it means to have an inverse function. And for this to work and be a function, the domain of it, the y, needs to be limited to negative pi over 2 to pi over 2. Okay, so if I go ahead and start with a function y equals tangent inverse of x, we don't know how to take a derivative of it yet, so I'm going to convert this using the inverse tangent rule to say tangent of y is equal to x, just as we saw above, and then take the derivative of both sides. And again, we're going to do the derivative of the left side implicitly. So I take a derivative of tangent of y on the left and derivative of x on the right side, both with respect to x. On the left side, again, if you recall, derivative of tangent is secant squared. So derivative of tangent of y would be secant squared of y. But then I need to use the chain rule. I'm doing things implicitly. I have a dy over dx. On the right side, the derivative of x is 1. And then we'll divide both sides by secant squared to isolate dy over dx. And then I'm going to use a little bit of trigonometry. So secant squared has a trig identity. We know that 1 plus tangent squared is equal to secant squared. So I can replace the secant squared of y with 1 plus tangent squared. And the point of doing that is so I can get things back to be in terms of x. And the second I get a tangent of y back in my problem, I have, well, tangent of y squared, or tangent squared of y, I can go back and replace tangent of y with x. So this becomes 1 plus x squared on the bottom. Right? And that gives us the formula for the derivative of a tangent, for the derivative of tangent inverse. The derivative of tangent inverse of x is 1 over x squared plus 1. Right? And that's going to be our formula. And we finally wrap this up by looking at an example. So here we want to take the derivative of tangent inverse of e to the x. So to start with, we'll use the formula for the derivative of tangent inverse and then multiply that by the derivative inside because chain rule is needed in this case. So derivative of tangent inverse of anything is 1 over that expression squared plus 1, right? So tangent inverse of e to the x would be e to the x squared plus 1. Then we're going to multiply by the derivative of the inside because of chain rule, so times e to the x. And just to clean it up, that gives us the derivative of the function we started with y prime is equal to e to the x over e to the x quantity squared. We can use the exponent rules and multiply the two exponents and get e to the 2x plus 1.